This is section 16.5, triple integrals in cylindrical and spherical coordinates. This section has 9 pages of notes, and it's really long, and it's really technical, and it's quite difficult. And so you might be thinking, no, not this section, it's terrible. But this is the section where we actually have finally got enough mathematics that we can deal with the fact that we live in 3 dimensions. We managed to get up to triple integrals in rectangular coordinates in the last section, where we thought of everything in terms of x, y, and z, but rectangular coordinates in 3 dimensions are just usually not the best way to deal with 3 dimensions. For example, if you have to give someone coordinates of where you live on Earth, you don't tell them, well, start at the center of the Earth, go toward the sun 3,000 miles, and then go out of the plane of the solar system by 4,000 miles. And that, no, this is not good. Instead, depending on where you are and what your situation is in 3 dimensions, you use different kinds of coordinates. In particular, on the Earth, we would use latitude, longitude, and altitude, which are called spherical coordinates, but we'll get to that. So this section, it is tricky, it is technical, it is difficult, but we live in 3 dimensions and we can finally deal with it, and this is how. So we're going to try to actually use these new coordinate systems. We'll learn how to convert between them, and then finally we'll evaluate integrals in these coordinates. The functions that we're using will usually be functions where the input is a point in space, and it just so happens that points in space are often best described by a latitude, a longitude, and an altitude, which is 2 angles, instead of 2 angles and a distance, instead of x, y, z, which is 3 distances. So let's do it. First is, let's remember how polar coordinates worked. If you have a point in polar coordinates, you can describe it by saying how far over you go and how far up you go. This is not in polar coordinates. This is rectangular coordinates, and you call the point xy. Or you can say, that's nice, instead I'll tell you how far to go from the origin and what angle from the positive x-axis you should go. And then you call the point r theta. And either one works just fine, and there's some equations that let you translate between them. This triangle contains all of these formulas. So if you're going to make a reference sheet for yourself, you could write down this box, but this box is just a list of all the facts that there are about this triangle. Cosine of theta is x over r. Yeah, that's this. Sine of theta is y over r. That's this. Tangent of theta is y over x. That's this. Pythagorean theorem is right here. So this picture is this box. Up to you. Okay, so this allows us to change any 2 coordinates into polar coordinates, any 2 rectangular coordinates into polar coordinates. If you take x, y, z rectangular space coordinates and change the x and y into polar coordinates, you get something called cylindrical coordinates. So you say, if I have a point up here, that I got to it by straight line. I got to it by going x in the x direction, y in the y direction, and z in the z direction. You get some point up here, call it x, y, z. In cylindrical coordinates, you leave the z alone, but you switch out the x and the y for polar coordinates r and theta. Here's r. And here's theta. And then you call the point r theta z. In rectangular coordinates, it would be called x, y, z. And in cylindrical coordinates, cylinder because a circular cylinder has it's round in the xy plane and it's straight in the z axis. So in cylindrical coordinates, the exact same point is called r theta z. And this picture just shows you everything about it, I guess. Yeah. So essentially all of the picture that tells you how to translate between polar and rectangular coordinates in 2 dimensions, those are all the same facts that there are about cylindrical coordinates. Because there's nothing extra going on other than what was going on in 2 dimensions. Okay, so let's practice. Here's something that by the second number being an angle, you can tell is in cylindrical coordinates. So let's convert it to rectangular coordinates. Well, z stays the same, because cylindrical and rectangular both have z in them. But here we have r is 3, and theta is 7 pi over 4. So we need to turn that into x and y to get to rectangular coordinates. Well, I have my understanding of how polar coordinates work, and my understanding of how polar coordinates work is this picture. If you want to memorize or have active all the time like this little box with all the formulas, that's fine, but I think that's a waste of your time. So I need to go over to theta is 7 pi over 4. That's almost 2 pi, which would be 8 pi over 4. So it's going to be all the way down here. And then I'm going 3 in this direction. Well, how do I go 3 in this direction? Well, I would need x to be 3 over root 2 and y to be 3 over root 2. If you like thinking this way, in this, oh crap, y here will be minus 3 over root 2. If you like thinking geometrically, just go for it and do it that way. If you want to use the formulas, you can. You would just say that x is r cosine theta. And that's 3 cosine of 7 pi over 4. And cosine of 7 pi over 4 is 1 over root 2, so you get the same answer. But like, these formulas are not like magical formulas. The formulas are just, they explain how triangles work. So anyway, the final answer is 3 over root 2 minus 3 over root 2, 4 in rectangular coordinates. This one, none of these are angles, so we assume it's rectangular coordinates from context. To convert it to cylindrical coordinates, I have to turn the x and the y into r and theta. I'll leave the z alone in cylindrical coordinates. So let's do that. I'm going to go over 4 and down 3. Theta is this angle. Or I could think of theta as the negative angle that goes down this way. Okay, how can I, well, okay, a 3, 4, 5 right triangle is a thing, so r is 5. If you used the formula, you'd use the Pythagorean theorem to do 3 squared plus 4 squared equals c squared, and you'd find c is 5. Then we need to figure out what this angle is. Well, whatever this angle is, the cosine of the angle is 4/5, and the sine of the angle is minus 3/5. But I need to come up with a name for this angle based on these. It's either going to be arc cosine of 4/5 or arc sine of minus 3/5. Those will be the easiest ways to write this angle. I guess arc cosine of 4/5 would land in the first quadrant, and I don't want that. So I'll use arc sine of minus 3/5. So I'll give this angle a name. Arc sine minus 3/5. Then we are, r is 5. The angle is arc sine minus 3/5, and z is 1. So I've converted my rectangular point to cylindrical coordinates, r, theta, z. Okay, let's see what equations look like when they're in cylindrical coordinates. When they're in rectangular coordinates, say you had y equals 4. Y equals 4 was a plane. But now what's like theta equals a number? Okay, well, in the xy plane, theta equals pi over 3 is a line where you go like pi over 3 up from the x-axis toward the y-axis. But theta equals pi over 3 doesn't mention anything about the z-axis, so you get a cylinder, meaning this theta equals pi over 3 occurs at every value of z. So it's a plane containing the z-axis. Like the z-axis. Oh no. Okay, which pen was I using? I think this one? No. Okay. I accidentally changed my pen. Maybe this one? Nope. This one looks good. So containing the z-axis. This is in the plane. Slices the z-axis. Okay, what would the graph of z equals 4 be? This is the same thing as it would be in rectangular coordinates, because the z coordinate does not get changed in cylindrical coordinates. It's a plane parallel to the xy plane. The one thing that I will change when I say this in cylindrical coordinates is that the xy plane is now called the r theta plane. Seems good. Okay, how would we get an equation for this? Well, it looks like whatever's going on with this cylinder, the equation will not mention z, because each slice at each z is all the same. So I'll need to have some kind of equation that only involves x and y in rectangular, that only involves r and theta in cylindrical. Well, it looks like it's a circle of radius 4. A circle of radius 4 in rectangular coordinates is x squared plus y squared equals 16. With no z in the equation, I'll get a cylinder with my circle copied at every level of z. In cylindrical coordinates, this is a lot easier to write it. You write it as r equals 4. So some shapes, of course, like round shapes, are easier in cylindrical coordinates, the same way that round shapes in the plane are easier in polar coordinates. Okay, what's going on here? What does r squared equals z squared plus 1 do? To figure this out, I think our best bet is probably to use our level curves plan, where we say, well, I don't know what it is. Let's try some values of z. So try z equals 0. When z is 0, you get r squared equals 1, which is a circle with radius 1. So in the xy plane, I've got a circle of radius 1. What about z equals 1 looks ugly. Oh, all the z's are going to be kind of ugly. Okay, if z is plus or minus 1, then I get r squared equals 2, which is a slightly larger circle. But it's larger when you go up or down. What if z is plus or minus 2? Now you have r squared is 5, so it's an even larger circle. What shape is this? This is a hyperboloid with one sheet. It's this thing that, in popular movies or TV shows, it would be like the picture of a wormhole, where there's a huge opening and it gets smaller and smaller, and there's a small opening, and then there's a big opening at the bottom. So this is a hyperboloid of one sheet. The main thing here is when you run across a weird looking equation, don't be afraid. Plug in 0 for some things and see what you get. Okay, this in rectangular coordinates gave us a circular paraboloid, meaning every horizontal cross section is a circle, but it makes a parabola shape as you go up. In cylindrical coordinates, the trick is that if you have x squared plus y squared equals r squared. I remember this because my picture for how these coordinates work is just a right triangle. And x squared plus y squared is r squared. So I'll just factor out the 1/9. And I see that this is z equals 1/9 r squared. So a paraboloid looks like z equals a number times r squared, and you'd get this nice paraboloid. So that's basically how cylindrical coordinates work. You leave z alone, you change x and y into r and theta, and you're basically just polar coordinates, but there's also a z there, and that's it. Spherical coordinates, a bit more complicated. So spherical coordinates are more like latitude and longitude, where this one is kind of like latitude, except it's latitude where the North Pole counts as 0. The equator is 90 degrees, and the South Pole is pi. So you look at a globe, you say, okay, here's my globe, I guess. The North Pole is we'll declare that to be latitude 0, even though real latitude, the way actual latitude works, is you'd say the equator is 0. But this is just how we will do latitude in spherical coordinates. 0 is the North Pole, and then everything along the equator is pi over 2. Up here, where we think of 45 degrees north, that would be 45 degrees, because it's 45 degrees from the North Pole. So you count latitude from the North Pole in spherical coordinates, and that's this phi. You say this Greek letter as phi. Theta is the regular old theta from polar coordinates, so that's longitude. And if you don't know how latitude and longitude work, I guess this is a good time to pause this video and just figure it out once and for all, because like you live on Earth. So just go figure it out. And then rho, this is not a P. This is it's kind of like a P in Greek, but it's more like an R in Greek, rho. And the reason we use R is because it's the radius. It's the distance from the center. We don't use R because say you had a point in space. R, we've already decided, stands for the distance in the xy plane. So in spherical coordinates, we can't use R again, because what I mean by R in spherical coordinates is this distance. So we say, here's R from polar coordinates. Here's theta from polar coordinates. We'll keep the theta, because that's longitude around the globe. But this distance is called rho, lowercase Greek r. Here's another right triangle. So what's going on here? We've got x, y, z. I've got r and theta and z, which was cylindrical coordinates. And then phi is your latitude measured from the North Pole. That's this angle. So spherical coordinates are your radius. This is your altitude. Your theta, that's longitude. And your phi, that's latitude but measured in a weird way. And that's this point. You can make this point rho, theta, phi. Let's see how it's described over here. Rho is the length, positive length of the line segment from the origin to the point. Yep, it's the distance. It's like an altitude, if you were thinking of the origin as the center of the Earth. Theta is the angle measured from the positive x-axis going counterclockwise, same theta as before. And then phi is the non-negative angle. It can't beat pi, because pi is the south pole, measured from the positive z-axis. Yep. So, that's that. I think the next page has like the formulas for spherical coordinates. Oh dear. Okay, well, since I have the triangles drawn here, let's just get them on here. So say you want to relate the various coordinate systems all to each other. The trick is that this picture has two right triangles, and those two right triangles determine everything about like all the relations between the various measurements. The only insight you have to have is something from a long time ago in geometry, which is that like this angle is theta. This angle is phi. So this angle is absolutely not phi. Instead, whenever you had one of these were called alternate interior angles, you got to say that this angle over here was repeated up here. So up here is also phi. So if you get these two right triangles, they have all of the different coordinates in them. So here's the polar coordinates one. It's got x, y, r, and theta. And then the one you need to add on in order to get spherical coordinates has r, z, rho, and then phi is kind of like floating up here, which is surprising. But these two right triangles contain all the formulas that have to do with all of the different coordinate systems in the entire class. So many people will have formula sheets or like boxes full of formulas that have a million things, and they'll have stuff like tangent theta equals y over x. But like that's what this triangle does. Or like tangent phi equals r over z. And I don't really see the benefit of writing down specifically that tangent phi is r over z. It's true, but like that's just in this triangle, and the triangle isn't that hard to draw. So I think that when we have When we're trying to do conversions, you should just draw these two triangles, and it's all here. I don't know. So let's move on and get these formulas. So this was, if we were in class, I would have you like go through these and like figure it out yourself. Okay, so x in our picture, let's just get the two pictures up here. This is not an answer to that question. I've got x, y, r, and theta. And then the other one has r, z, rho, and phi. So you want a formula for x? Well, your formula for x will have to come from this triangle, and it'll be the cosine of theta because it's adjacent to the theta. So x will be r cosine theta. Y will be r sine theta. And then how do you get z? Well, it's adjacent to the angle phi, so it'll involve the cosine of phi. So it's going to be rho cosine phi. Notice the difference between theta and phi. It's kind of a big deal. Okay, if you do x squared plus y squared, you get r squared. And then if you do r squared plus z squared, you get rho squared. So that's this formula. And then, like, I guess we can write down what the tangent of theta is. It's y over x. And phi is the arc cosine of z over, this is just rho from this. So this is phi is arc cosine z over rho. Then there's a bunch of things written in these notes that are all about like various tricks for dealing with the different variables, but like it's all in those pictures. There's no information other than these pictures. Like so I don't really see the benefit of writing 13 formulas. So let's actually work with some spherical coordinates. So rho equals 5. What is that? Well, that's a sphere with radius 5. Notice that if you instead said r is 5, that's a cylinder of radius 5. So if you pick the radius in cylindrical coordinates and just set it to a number, you get a cylinder. If you pick the radius, remember this is a Greek r. If you pick the radius in spherical coordinates and give it a number, you get a sphere. That's like what those words. Okay, theta equals pi over 4. We did this before with theta equals pi over 3. This is a plane containing the z-axis. Phi equals pi over 4 is a little bit different. Phi equals pi over 4 is like you imagine the whole Earth and you pick a latitude of 45 degrees from north in all directions. What you get is a cone. Remember, phi is measured from the North Pole. So this is pi over 4. And this is the cone that you get. It goes forever. Rho equals phi. Whoa. Okay, not sure what this is going to be. To figure this out, I'm just going to try some values of phi. So when phi is 0, rho is 0. What are some nice values of phi to draw? It's latitude. So the easiest are going to be like 45 degrees, 90 degrees. So I'll just do pi over 4, pi over 2, 3 pi over 4, and the biggest possible phi is pi. Okay, the function is pretty simple. It's just rho equals phi. So let's see what we get. At phi equals 0, we get rho equals 0, which is right here. When you let yourself go out onto this cone, you get to go further out. So I guess that gives you a circle. And then when rho is pi over 2, you get to go even further out. When rho is 3 pi over 4, you're even bigger. 3 pi over 4 is like down this way. And when phi is pi, so when you're in the South Pole, you get to be pi away from the center. So it looks like you're going to get some kind of like, I don't know, like a cake, like a bundt cake. I think everything looks like a cake. What a weird thing. Is this supposed to be like a normal object? I don't see it. Let's go to GeoGebra. That's not how you spell that. Let's hope GeoGebra knows how to do this. Phi equal, or no, rho equals phi. It has no idea how to do that. Let's see if Wolfram Alpha knows how to do it. Line? No, it's not. Don't lie. Yeah, well, if you make the axes phi and rho, then it's a line, but that's like pretty pointless. Okay, let's see if we can get a spherical plot. R as a function of coordinates. So I want spherical plot 3D phi theta phi, because rho equals phi. No. Huh. I don't know how to get a computer to do this. That's real awkward. It definitely like comes down to a point in the middle. Do I have a picture of it that someone else has ever drawn? Here's the picture I have of it that I had somebody else, from someone else who has done this class before, this thing. It's pretty similar to my picture. It basically like comes into a point in the middle, and then it like kind of blossoms out and goes down. It gets really big around the base though. Like this needs to be a lot fatter down here because rho is 3 pi over 4 down here. So you need to be like really far out. But yeah. Okay. The point here, again, is just like, don't be afraid when you have a weird formula. Just like plug in some numbers into the things and see what happens. Next page. Okay, the point of this was not just to use spherical coordinates and convert between them at the top. We are also trying to actually do some integrals with these coordinates. So how does that work? Like, what do we do? Well, we've already dealt with how to deal with like changing from xy to r theta. So what we'll have to do in this section, we'll have to do it twice, is we'll twice have to make a geometric argument of what happens when you slice up the world using your coordinates. When you slice up space using x, y, and z coordinates, you get little boxes. So this was rectangular. You got little boxes, dv, which were dx times dy times dz. But now in cylindrical, we don't get boxes anymore because we're cutting things up with like r and theta. So we're getting this picture that we had in the polar coordinates section where you've got like a little bit of theta and like how long is this? But that's no problem. We already dealt with that. Dx dy can be rewritten as r dr d theta, and we're leaving z alone. So when you integrate a function, dv, and you want to do it in cylindrical coordinates, you just leave the function alone, except, I mean, you need to convert it to r, theta, and z. But then dv can be written as r dr d theta dz. So this argument that we need to make for cylindrical coordinates, we just can copy the argument from before, that this area of this little box is r dr d theta instead of just dr d theta. And then we just multiply by dz because we're leaving the z's alone. So when you convert, when you do a triple integral, this isn't actually a conversion. When you do a triple integral in cylindrical coordinates, this is dv. It has an extra r on it. When we do the argument for spherical coordinates, it's going to be a little bit crazier, but we'll get there. I'm not doing this. Okay. So let's set up a triple integral using cylindrical coordinates. So we're bounded above by, oh, we've seen this before. We drew this like 1 or 2 sections ago, I think. Z equals 1 minus x squared minus y squared is this paraboloid. It's got a circle on the bottom. And then z equals 1 minus y was like slicing it this way. And when we looked down on the xy plane, it made a circle of radius 1/2. So let's try to find the volume, and we'll find the volume this time in cylindrical coordinates. So the volume is integrate over the region, dv. There's no function here when we're finding the volume. Instead, we're just adding up all the little bits of volume to get the volume. Well, dv in cylindrical coordinates has a form, and that form is r dr d theta dz. Now, we can put this in any order we want, as long as we're careful about the order that we end up with in the, like, inside our integral. And it will turn out that it's just most often the best to get the z first, to get the z on the inside. Now, this choice of which order to do this, it matters a lot. And if you choose an order and you end up not being able to do the integral, you need to choose a different order. But, yeah. I think I'm wrong here. I don't think this is a nice order. Is it? No, this is fine. Basically, just keep your mind open about whether you like your order or not. So what we should do is, when we're setting up the bounds, you first deal with the outermost bounds. But in the past, usually our outermost bounds were like dx, dy, and so we were looking at the xy plane to figure out what to do with our outermost bounds. Here, I'm keeping that alive, where my outermost bounds aren't x and y, but I can think of the same thing being in the r theta plane, and so I deal with those first. So in this, if we think about this shape in the r theta plane, and I hinted at this in that section long ago, this circle has an equation of r equals sine theta. R equals cosine theta would be over here on the x-axis. So my r bounds are going to go from, well, 0, r equals 0, out to r equals sine theta. But what about my theta bounds? Well, this circle, you say, oh, it's a circle, it goes all the way around. But no, that's not what theta does. Here's theta equals 0. And here's like theta equals pi over 2. And the circle stops at theta equals pi. This, in the xy plane, in the r theta plane, there's nothing going on after theta equals pi. So the theta bounds are actually 0 to pi. Now we can get the other bounds, like the z bounds. The z bounds, we need a lower z function and an upper z function. The lower z function is this 1 minus y, and the upper z function is this one. But I don't like this one. I guess I don't really like this one either, but let's put them in there for now. The reason I don't like these bounds is that I need these bounds to be in terms of the outer two variables, namely they need to be in terms of r and theta. So to finish like setting this integral up, I need to notice that I need to turn the x's and y's into r's and thetas. So x squared plus y squared is r squared, is going to let me deal with the top bound, and then y equals r sine theta lets me deal with the bottom bound. So the integral I would have to do to find the volume of this like weird slice in cylindrical coordinates is 0 to pi, 0 to r sine theta. What? No. r equals sine theta. R equals sine theta. The second bounds have to only depend on the outermost variable. So 0 to pi, 0 to sine theta, and then 1 minus r sine theta to 1 minus r squared of r dz dr d theta. So this is my setup. Because the integral is kind of a mess in rectangular coordinates and it's kind of a mess in cylindrical coordinates, we go like, whatever. And then you just pick one and do it. But this question just told me to set it up, so that's all I did. Okay, so that was cylindrical triple integrals. Now we're going to deal with spherical triple integrals. In order to get this going, we need to figure out what dv equals in spherical coordinates. dv was r dr d theta dz in cylindrical coordinates. So we had our earliest dv was like dx dy dz. And then our next one was replace the dx dy with r dr d theta, but leave z alone. Now we're getting a new one, and this one is spherical triple integrals. So you slice everything up in latitude and longitude slices, like the way that you would slice up the Earth with like actual latitude longitude lines. Can I like... I had one available. Oh no. I just want the image. Sorry. So if you take the Earth and you slice it along latitude and longitude lines, that's along phi and theta. That's the phi and theta coordinates. And then the rho coordinates are like shells of the Earth. So you'd have like the core of the Earth, and then like a little bit further out and a little bit further out, bigger and bigger radius spheres in spherical coordinates would be the slices in the rho direction. So we're going to get these like little wedges on the like out of spheres, and I want to know what is the volume of a little tiny wedge of like a little bit of latitude, a little bit of longitude, and a little bit of radius. What do you end up with? Well, here it is. So you it's all filled in already, so it looks super complicated. Okay, well, you're gonna have a little bit of theta, so that's this. That makes sense. And you're going to have a little bit of phi, and you're going to have a little bit of rho. That's what we're trying to figure out. We want to know what dv is in terms of d theta, d phi, and d rho. Well, dv is the volume of this weird thing, which is kind of boxy. We just need to figure out all of these dimensions. So here's one dimension. It's, well, we're going a little bit of rho, a little bit of phi, and we're out by a distance of rho. So this thing is definitely rho d phi. That's this right here. What's going on down here? Well, I mean, I need to know this distance and multiply it by d theta to get this distance. But this distance isn't r because r is not available in spherical. So we figure out what r is from our little diagram of how spherical works. This is r rho phi. So r, this distance, is rho sine phi. That's this. So since this length, so this area is r dr d theta. Is this right? No. It is right. think this image works. Okay, well, I figured out what is wrong with the image. The image is wrong, but like the final answer is right. So let's fix the image and get it right. So this area is RD theta, which is what the arrow is pointing to, but that's not what we want to do at all, actually. So I guess I'll have to go like go to this open source picture and try to fix it later. RD theta is right here. RD theta is this length. And that length is what we actually want. So when we find r d theta, r is rho sine phi. So here's rho sine phi d theta. That is this length. So this little box, it's got rho sine phi d theta, rho d phi, and d rho. And if I multiply all those together, I get dv. So these arrows are just pointing to the wrong place. But if you multiply all these together, you get 2 copies of rho, you get a sine phi, and then you get 1 of each of the d things. So my final answer for dv is going to be rho squared sine phi, d rho, d phi, d theta. Again, this is not really a conversion. This is just how spherical integrals work. If you have a function and you're integrating the function over a 3-dimensional region, over a solid region, you still integrate over the same region. You have to change the function so that it's all in terms of spherical coordinates. And then dv equals rho squared sine phi, d rho, d phi, d theta. This thing is called the Jacobian, and when we do like crazier changes of variables, which I'm not sure we even do in this class actually, but if you ever need to do crazier changes of variables, you'll have a general formula for the Jacobian, and it comes out to this. Anyway, this is how spherical integrals work. This example 8 is supposed to be an example to convince you that spherical coordinates are a good thing, but it turns out that this particular example, it just shows you that like substitutions are good. So instead of doing this example, if you want to know how to do this example, by the way, what you do is you let u equal x over a, you let v equal y over b, and you let w equal z over c, and then you'll find that the whole integral is very easy. But just to show you one simple example where you can actually use spherical coordinates and it is easy to use, I'm not going to do this one at all. Instead, we'll just use spherical coordinates to find the volume of a sphere. Let's just do the sphere of radius r. That's x squared plus y squared plus z squared is less than or equal to, and we'll pick some number for the radius, r squared, capital R. Most of the r's are taken. Lowercase r is reserved for cylindrical and polar coordinates. The Greek letter r is reserved for, yeah, it's all reserved, but whatever. So when you do this, if you were going, we can still look at kind of the same kind of picture where we're going to set up the volume as the integral over the region of all the little bits of volume. But since it's a sphere, you should suspect that spherical coordinates are useful. So yeah, I'll use the dv of spherical coordinates, which is rho squared sine phi, do we know what order is good? I guess it doesn't matter. D rho, d phi, d theta. The order that you choose affects what bounds you will end up with. If you ever choose an order and you don't like it, you just try a different order. Now the bounds describe the region. So the region here is now a solid sphere. So you ask, okay, the outermost one, what's the lowest theta and what's the highest theta? Well, for a sphere, the lowest theta is theta equals 0, and you can go all the way around, theta is like longitude, the highest theta is 2 pi. So theta goes from 0 to 2 pi. What about phi? Well, phi is like latitude, except it's measured from the North Pole. So the lowest phi is 0, and the highest phi is all the way down at the South Pole at pi. Those are the phi bounds. And then the rho bounds, well, rho is the radius, like in perspective of a sphere. The radius is going all the way out to capital R. Since all of the bounds were just numbers, that means that we could easily just switch around all of the order if we wanted to, and it would be fine. But let's just leave it like this, because it seems fine to me. And then we'll actually finish this integral in terms of spherical coordinates. So we have to do the rho integral first. Sine phi is a constant in this integral. And all the other integrals are sitting here waiting for us. The integral of rho squared sine phi keeps the sine phi. Integral of rho squared is 1/3 rho cubed. And we go from rho is 0 to r. So I get 1/3 r cubed sine phi, d phi d theta. Now I can do the phi integral. 1/3 r cubed is a constant. The integral of sine phi is minus cosine phi. Not sure where to go. I guess we'll go over here. Poor planning on my part. So the outer integral, the theta integral, is just waiting for us. The 1/3 r cubed is a constant. The integral of sine phi is minus cosine phi. And we're going to go from 0 to pi. So you plug in pi, you get minus minus 1. So you get minus 2. Right? Wait, minus minus 1 is not minus 2. Minus minus 1 is 1. Okay, so you get 1 minus 1. So you get 0. This seems bad. I guess I'll write it out slower. So I have 1/3 r cubed. I'm going to have minus cosine pi plus cosine 0. Like, I know I don't want the volume to be 0, so when I try to do something fast and I get an answer that's nonsense, then I like do it slow instead. So this is just 1 plus 1, so this is 2. So I have integral of 2/3 r cubed d theta. Well, this integral, there's no thetas in here, so the integral just multiplies the whole thing by 2 pi. So I have 2 pi times 2/3 r cubed, and I end up with 4/3 pi r cubed, which is what I was expecting. So this means that, like, the spherical coordinates, integrals with spherical coordinates, they work well on spheres. It will turn out that if you wanted to do the original example 8 that was written here, some substitutions would let you use spherical coordinates, but like that problem was dominated by the substitutions, and so we didn't do that specific problem. Okay, let's set up one integral 3 different ways using the 3 different coordinate systems. Generally, you'll like rectangular because it's familiar. You'll like cylindrical if things are round but not like spherical. And you'll like spherical if everything is spherical. So cylindrical, I feel like, ends up coming up the most, just because usually something is a little bit round, but it's not a perfect sphere. So let's set up the triple integral 3 different ways. So the bottom of the region is the plane z equals 2. So that's the bottom. And then the top of our region is z equals square root of 25 minus x squared minus y squared. What is that shape? That's either a sphere or it's like a paraboloid. In order to figure it out, I'm going to square both sides just to try to get the right picture. And then add everything over. That's a sphere of radius 5. So you go up to 5, and you'll have a sphere like this. So the region is a sphere where you've just like cut off the top of, like you just slice off the top of the Earth and you go like, here you go. What's the volume? Okay, in rectangular coordinates, you say, I am interested in finding the volume. The volume is the integral of dv, and dv has, my easiest rectangular form is usually dz dy dx. I'll put off dealing with z until later. First, I'll deal with x and y. So I look down on the xy plane and I say, what's going on when I look down from above? And the outer thing that I'll see is this circle when I look on the xy plane. It's a circle. The question is, which circle? To figure that out, I have the intersection of a sphere and a plane, so I'll just like plug one into the other, do a substitution to see what circle it is. So this is 2 equals square root 25 minus x squared minus y squared. Square both sides. Oh dear. It's x squared plus y squared equals 21. So it's a circle with radius square root of 21. So x goes from minus square root of 21 to square root of 21. That's too bad. Then in the xy plane, the bottom function is the bottom of this circle. So I would like solve for y. Y is plus or minus the square root of 21 minus x squared. So the bottom function y for y is this one. And the top function is the positive version. And this is the dy. So the outermost bounds, if you have x and y as your outermost variables, that's like what the region looks like when you look down on the region from above and see it in the xy plane. Then the z bounds, you do the bottom surface, which here is z equals 2, and the top surface, which is this thing, square root 25 minus x squared minus y squared. This describes this shape in rectangular coordinates. It tells you the lowest x and the highest x as numbers, the lowest y and the highest y in terms of x, and the lowest z and the highest z in terms of x and y. So this is the rectangular setup. If you had to do this integral, I hope you would never do this integral. I hope you would be like, whoa, this clearly needs some polar action. So let's try cylindrical. Since one of the bounds, one of the surfaces is a literal sphere, we're probably going to like spherical coordinates the best, but we'll see. So for cylindrical coordinates, same start. This is how all of calculus works. You want to find a thing, you integrate the little bits of the thing. But in cylindrical coordinates, dv is r, and then we've been going with dz, dr, d theta as our easiest order. I will start by attacking the xy plane as before, but it's called the r theta plane now, and it's a little bit easier because this base in the r theta plane is just... I'm getting a spam call, so I'm sorry if you can hear that. No, maybe you can't. Whatever. Okay, so it's r goes from 0 to square root of 21, and theta goes from 0 to 2 pi. That's in the r and theta plane. So let's just get that plugged in. The theta bounds are on the outside. The r bounds are next. And then the z bounds, well, z goes from 2 to square root of 25 minus some stuff. But notice that it's 25 minus x squared minus y squared. X squared plus y squared is r squared. So my cylindrical setup, when you're done, you'll have only r's, thetas, and z's in it. And my cylindrical setup is like significantly easier than my rectangular setup. So far cylindrical, definitely the best. I kind of think this is probably as good as we're going to get, but let's see. Let's try spherical. To set up spherical, we do the same plan. We say, I want to find a thing. It's the integral of the little bits of the thing. But in spherical coordinates, dv equals rho squared sine phi. D rho d phi d theta. I don't really have a favorite order here. I feel like I should have a favorite order. Huh. Yeah, I really don't. Okay, well, let's try to get the bounds figured out. So this thing, this shape, theta definitely goes all the way around from 0 to 2 pi. So that's the easy part. That's our theta bounds. For phi, well, phi starts up at the North Pole, and the North Pole is phi equals 0. It's up here. Phi equals 0. But then it goes all the way down to this value of phi. That's the maximum value of phi. So my phi bounds will be from 0 to whatever that angle is. So we'll have to do a little bit of geometry to get that angle. This point, we know a lot about that point. That point is like the outermost point, and that point has r is square root of 21. Do we know anything else about it? Oh, z is 2. This, combined with the picture we have that lets us convert between coordinate systems, should let us find this maximum value of phi. So let's just pull out our triangle, which is everything we know about convergence. It's got r, z, phi, and rho. Is that enough? Yeah, that is enough. We can figure out what phi is because we know r and z. So phi is arctan of, the tangent of phi here would be r over z. So r over z is root 21 over 2. Okay, no thanks. If I actually have to find this volume, I'm all in on cylindrical. But whatever, we'll finish setting it up. That's the phi bounds. Then let's get the rho bounds. Am I going to be able to get the rho bounds? I need to turn z equals 2 into something in spherical coordinates. The outermost bound, the like furthest out you can get, is the sphere of radius 5. So that's good. Like that's rho equals 5. But the plane z equals 2 seems a little bit tough. So let's try to get z equals 2 in spherical coordinates. If z is 2, what does that mean? Well, z looks like it's adjacent to phi, so z is rho sine phi equals 2. Well, not sine. Z is adjacent to phi, so it's rho cosine phi. Well, we're trying to solve for rho, so I guess you divide both sides by cosine phi, and you get rho is 2 secant phi. So this is the lowest bound for rho. So z equals 2. It turns out you can write it in spherical coordinates. I hadn't seen this before, but whatever. As rho equals, I don't have to write rho equals there. It's 2 secant phi. So all these triple integrals, this one in spherical, this one in cylindrical, and this one in rectangular, all give you the same answer. They all give you the volume of this like sliced off northern part of the, it's like you get just the Arctic Circle and above of the Earth. If you had to find that volume, which one would you do? You do the one that looks the least ridiculous, and in that case, it's definitely the cylindrical one. The cylindrical one is just usually the best. I don't know. I don't know why that happens. Like, you need everything to be made of spheres for the spherical one to be the best. Nice. I like the different coordinates. I mean, they're technical, and some people find them just straight up obnoxious, but you should feel like you live in 3 dimensions. Even dealing with 2 dimensions is tricky, and our only way to deal with that was to like draw right triangles and often use polar coordinates. To be able to actually deal with 3 dimensions, it's just great. It means you're actually able to attack the real world with calculus, so it's really good. Okay, let's set up the triple integral that builds this ice cream cone. So this is z equals r. What does z equals r look like? It's a cone like this. And then x squared plus y squared plus z squared equals 4 is a sphere of radius 2. So the shape that we're looking at here is this one. This is sphere of radius 2. This is cone z equals r. And I'm mixing up all the different coordinates here, and it doesn't matter, it's fine. We'll deal with it as we go. So we set it, this question says, set it up in all 3 coordinate systems, and then pick one and actually do it. This is very round, so it's almost guaranteed that we will not be happy with rectangular coordinates. We might actually like spherical this time. Let's see how it goes. So here's rectangular. In rectangular coordinates, we're going to let v be the integral of dv, and our favorite form of dv is dz dy dx. To figure out what's going on with the x and the y, we draw the xy plane. And we look down on this cone from above, and if you look down on this cone from above, you'll see this circle as the furthest out thing that happens. Like the outer bounds of the shape. What is that? Well, you could plug in z squared equals x squared plus y squared, and you'd get, like I'm just plugging one of the equations into the other to solve for their intersection. So I end up with x squared plus y squared plus, and then z squared is another x squared plus y squared equals 4. If I divide both sides by 2, I'll get x squared plus y squared equals 2. So this is a circle with radius square root of 2. So the x bounds are, well, x goes from minus square root of 2 to square root of 2. Y goes from minus square root 2 minus x squared to square root 2 minus x squared. Gross. And then that covers the xy plane, so that covers the x and y bounds. Then the z bounds, well, the lower limit of the shape would be this thing, which is z equals square root x squared plus y squared. And the upper bound would be whatever this is solved for z, which is, well, you solve the sphere for z, and you'll get square root 4 minus x squared minus y squared. And this is all dz, dy, dx. I have no interest in doing this integral, but if we did it, we would get the answer. We'd get the volume of the ice cream cone. So, no thanks. Let's try cylindrical. Again, the setup will be kind of the same as with rectangular, where we're going to focus on the xy, or in this case, r theta plane to start. But our setup is v is the integral of dv. dv is r dz dr d theta. R and theta come from this circle, which is a lot easier to write in cylindrical coordinates. Theta goes all the way around from 0 to 2 pi. And r goes from 0 to square root of 2. Meanwhile, z is still kind of a mess, except that square root x squared plus y squared is r. And this is square root 4 minus r squared. So this doesn't look that bad. I'm kind of into it. Like, I feel like cylindrical coordinates might work. But let's try spherical just in case it's awesome. V is the integral of dv, which is, well, what does dv equal? We had some weird geometric argument that told us dv is rho squared sine phi, d rho d theta d phi. Let's try to get these bounds. Well, phi is like latitude measured from the North Pole, and for this ice cream cone, the lowest phi is phi equals 0, and we get all the way down to 45 degrees. So the phi bounds are pretty awesome. It's 0 to 45 degrees, pi over 4. The theta bounds, this cone goes all the way around. So theta goes from 0 to pi over 2. Whoops. All the way around. All the way around goes from 0 to 2 pi. Once you've done that, what are the rho bounds? Well, the lowest rho is down here at rho equals 0, and the outermost bound is just rho equals 2. So it turns out that in spherical coordinates, this is just awesome. The bounds are all numbers. So I was definitely in for the cylindrical integral, but it turns out that the spherical integral is just way better. You pick based on the bounds. Like, these bounds are all numbers, so I'm in for this integral. So we'll find the volume using this one. So we'll do the phi integral first, leaving the outer integrals alone. Sine phi is a constant. Integral of rho squared d rho is 1/3 rho cubed. And we're going from 0 to 2. So these outer integrals are still waiting for us. When I plug in the 2, I just get 8/3 sine phi. This integral doesn't have theta in it, so an integral from 0 to 2 pi of this thing d theta just multiplies by 2 pi. So I just have now 16 pi thirds, and I still have a sine phi. Now integral of sine phi is minus cosine phi, and as you saw earlier in this video, I should not do this quickly. From 0 to pi over 4. Luckily I have minus minus, so this cancels. Wait, where was this minus from? There's no minus there. Integral of sine phi is minus cosine phi, so I'll just keep this minus. So what do I have? 16 pi over 3 times minus cosine pi over 4 minus cosine 0, so plus 1. So this looks like my final answer. I'm going to need to verify that this is a positive number, otherwise I'm very unhappy. Yeah, square root of 2 over 2 is like 0.7, so this is a positive number. So this is the volume of this ice cream cone. Nice. Spherical coordinates were awesome for that. Yeah, that matches my answer from my prep. Okay, so this is spherical and cylindrical coordinates. I think that's the end of it. This video is like more than an hour, so sorry about that. But hopefully you got the idea that when we're dealing with 3 dimensions, sometimes shapes are better described in other coordinates, and the other coordinates we have are cylindrical, which is basically polar coordinates, and spherical, which is like actually designed just for 3 dimensions and is kind of like latitude and longitude. When you put it all together, all the information about the different coordinates is encoded in these triangles. But if you prefer huge lists of equations, you can write down every fact about these triangles and call it the conversions between cylindrical and spherical and rectangular. Then we did a bunch of examples of how to deal with them. Watching those, I don't know if that's like painful or like amusing or just like amazing. I don't know what it is, but you need to do a bunch of them. So go do a bunch of stuff with these and go get stuck and ask questions and then become more expert. Yeah. We have one more section of applications of this that we'll do after this. So see you for that one.